Couple things. Okay, people have heard my wording from one class. I'll give my wording here. Okay, if you're taking one of my exams and you have another class.
Oh Lord.
Okay. Yes. Okay. I'm not referring to anyone in particular. I don't know who I possibly be referring to. Okay.
Oh.
Go to the class. Okay. The way I have it set up is that you can actually leave your exam there, go and come back. Do not skip Dr. Kirtland's advanced lab, even if you have one of my tests, because then I hear about it.
Okay.
And I don't want to deal with it. Okay. Not that I'm talking to anyone in general. Possibly. Okay. If you're taking my exam and he's teaching class, go to the class. Okay. Yeah. Okay. Sure. Okay. If I come by and you realize you're not in the class, I will physically move you to the. I will take away your exam, leave you in your chair, move the chair physically there into the advanced lab, and go from there. Okay. So, just not that would happen. Just just in case anyone was thinking about not going to the class. Okay. So let's go on with. Oh, I have to tell you about why that the 100% polarization is working. Okay, so let's go back to our Brewster's angle thingy. Okay, also called the polarization angle. Okay, so when does that occur? Not what it's going to do, but when do you have Brewster's angle? When what and what?
When the sin angle is equal to the no.
Well, that's always the case. Okay, so if you have your normal here, here's your surface. This is N1, N2. You have this right here, which is called the incident ray. So let's say this is the polarization angle. The reflected ray has to be, and it always has to be, has to be the same, and you're going to prove that in homework 4 here. And then here's this right here. What do we call this right here? The refractive ray.
Okay, so it's when the incident angle is equal to the refractive.
No.
Oh no, it's no. It's when but it's when the difference. No, it's when the distant angle between the refractive light and the refracted light is 90 degrees.
Okay. Yeah, this has to be 90 degrees. Yeah. Then you actually then have the polarization angle or Brewster's angle. The claim is that if this is unpolarized light, if this light over here is going to be 100% linear polarized. And the way it's going to be is that this is going to be into and out of the page. So what this represents here, that X and the dot, means that if the light's going this way, that electric field's going like this. Okay. So if I'm here, and I have on my cool shades, how would my transmission axis go if I'm blocking this? How would I want my transmission axis? I don't want flare.
What was the question?
Okay, I'm wearing my polarized sunglasses and I don't want glare. How do I want the transmission axis to go? Yeah, I want the transmission axis here to be like that. Maybe vertical, and that would have been blind. Okay, so let me give you an argument for why this is the case. So why is the reflected ray 100% linear polarized? Okay. Let's go back to Rayleigh scattering. So recall, Rayleigh scattering. So here's our little atom, like this. Here's our little electron. Here's our, I'll just say here's my dipole. Here's my P. Here's my incident wave. what's it gonna do? It's gonna make this dipole oscillate like this. And where do you get no, how does this look? We said that this is actually, if you look at the intensity, take this dumbbell and kind of rotate it around like this. And what did we say? We said we have no light here, no light here, no light. No scattered light. And also down below here, there's no scattered light. Okay. Now, how does this all tie together? So let's look over here. Let's say these two are 90 degrees. Let's say the light is linear polarized like this. So this is linear polarized in the incident plane. So the electric field's going like that. That means when it's in here, the electric field is also going like this. Okay. That means that this dipole here is oscillating like this. What do you know about this direction and that direction? They're in the same direction, but there's no light emitted. Okay. This is going like that, there's no light. Where if you have this, this is linear polarized perpendicular to the incident. This, like that. Now you have this, and not like that. And that actually, remember, this is going to be this case over here. That's going to be your maximum reflection. But this will also then give you. Okay, so what you can do is any incident, any unpolarized light that's coming in, I can always break it up into part that's parallel to the plane, that's within the plane of incidence and perpendicular to the plane of incidence. And any of the part in the plane of incidence that does not be scattered. Pretty simple. Questions? Okay. Now, we're going to do another one. Look at daily homework. Give us something. Okay. You are going to do an example of Fermat's principle here. And this is going to be for a spherical surface. So I want to talk about spherical surfaces. In daily homework 7, is that showing up? Yes, it is. You will work out what happens when light travels through a spherical surface. So let's see what we have here. So I'm going to have, this is a sphere right here. So imagine I take like a compass and I make an arc here like this. So this is going to have some radius here, R. This R is your radius of curvature. Radius of curvature for the spherical surface. And this right here, this is going to be this will have some index refraction. Do I call it N2 in there? What do I call it? N2. And this is going to have some index refraction N1. Okay. Again, this is, imagine you rotate this. So this whole thing here is just one big piece of glass. Doesn't matter. Okay. The question is, if I'm over here, I'm here. I'm gonna call the distance from here to that very center here. I'm gonna call this S0. Without S0 there, I'm talking to.
Yes.
I do. Okay, that's gonna be S0. This is ultimately going to become the object distance, but we don't know that yet. And we're going to look at rays really close to this axis here. This right here. Okay, we're going to call this thing with your alpha. We're going to assume small alpha. So basically, these rays are not going too far from. Now, what's going to happen? It's going to go in here. There's my normal, and then it's going to bend. And let's say it's going to go like that. And then I call this thing with your theta. And you're going to call from here, in other words, from that point here to there, and you call that SI. Yes, I do. You will show. You will show. Using Fermat's principle. Okay. And Snell's law. That. Okay. And you're going to show that this, you're going to get this little equation down here. You're going to show that N1 over S0 plus N2 over SI equals N2 minus N1 over R. You're going to prove that. Okay. That'd be a nice application of Fermat's principle. We have to use the law of cosines and other jazz. What's the law of cosines?
Oh, squared.
This is A, B, C.
B squared. Okay, my bad. C squared
C squared.
equal A squared plus B squared minus AB cosine theta.
That's 2AB.
Not 2AB.
How does it prove it? Can you?
Just a right triangle.
Turns out it's not. This is actually true for.
Yeah, no, I just put it out. Oh, farming principle?
If I just remembered wrong, I thought it was square root of all the a squared plus b squared over.
I mean, if you want to follow yourself.
Oh, wait, d squared, never mind, yeah. Okay.
So actually, now that you're all grown up.
Yep.
Give me the easy way to do it. You're all grown up.
Let's assume an ideal case and let's just assume C equals 0.
And this is A. I call this the A vector. I call this the B vector. I call this theta. What would be this vector right here? I'll call this C.
It will be A plus B.
Okay, so A plus C equals B. So C is
B minus A.
B minus A. Okay, prove it. Easy peasy now.
Can we first do the magnitude of C?
No.
No. Okay.
I could take C and dot it into itself.
Oh, so when you dot it over itself, doesn't it give you the magnitude of C?
Well, yeah, but not with your problem. Okay. So this is, that will be your C squared. B dot D is B squared. Minus A dot minus A is A squared. But then what do I get twice across? Minus 2A dot B. What is A dot B?
A, B plus
A, negative B. This is just A squared, B squared, minus 2AB. Okay. Pretty simple. Okay. What? But there's always a painful way to prove it. Why are you doing it that way? I don't know. Okay, now what are we gonna do with this right here? From this, we're gonna make a circle lens. So let's use this result. Let's use this result to calculate the no, it's not to derive the thin lens equation. Okay. So what we're going to do, we're going to actually use what's called a thin circle. We're going to use a circle lens. So consider a spherical lens. That is thin. Okay, so let's figure out what a spherical lens is. So what do you think a spherical lens is? So in other words, this is going to be one part of a sphere here. So I'll have this side, I'll have basically this here. So this has some R, what am I calling this? Now turn to this convoluted picture here. I'm calling that side here, I'm calling that side here R1. Okay. So what this is showing you here is, again, if I had a compass like this, I can take a compass and I can go like this. So I'm considering this part here, I'm calling this side here R1. Okay. Now what I can do, I can then come over here and I can make another circle like this. And then I can say that this has some radius here, R2. So this is actually going to be a circle. Okay. What do you think it means to be thin? It means that this part right here is going to be small. Does it have a name? That's just called D. So D, if D is small, we have a thin spherical lens. And what I want to do is derive something called the lens equation. In other words, I want to figure out where an object is going to be. I had like 8,000 students coming back to office hours today from barrel physics. So I did not get enough time to get lenses set up for them. Let me go grab something just a second. But let me. Everyone's played with lenses? Yeah, I know you have glasses, but have you? No, there needs to be really refining.
Yeah, you get, you don't get glasses, that's okay.
So in here, if you have bad vision, you're just bad.
What? You're about big fight?
Yeah, you're like,
Oh,
oh, guys,
oh, it's
yours. Yeah, not really.
You can't talk shit.
Yeah.
I just think it's not my fault that you
Nah,
have bad vision.
I thought you shut up.
I just want to say, I'm not saying anything about anybody's vision.
Yeah.
I'm
No
I'm
comment
saying
from me.
y'all's vision on that.
Oh, sorry. Don't worry about it. This is for-
Want to stick a photo?
Yeah,
Why do you do that easier?
I don't know. I feel like it would be. I mean, it's like if the physics do that.
Sticking a fork in an outlet.
Yeah. But
Oh, some-
I must have missed that.
I have no idea whether these are going to work because I just kind of grabbed them.
it would do that.
Okay, you're gonna.
Oh
So
my God.
try doing the try.
You're huge.
Okay, let's do a field trip. Take a white piece of paper.
Yes.
And let's go out to the atrium. We're gonna go out. Take a white piece and your lens.
Make the homework. We're going out.
Sorry, Zephyr, we went outside. Okay, so with that said, that's what we want to do now is actually look at something like this. And so there's going to be kind of a couple little weird sign conventions. I want to talk about what the sign conventions are, and then we'll get from there. So before we actually okay, so before we derive the Thin-Lens equation, we need some sign conventions. I think that's getting way too faint, and I don't even know if people can see that. They can still see that. That's good. I declare it done. Okay, so here's a convention here. I'm going to assume that the light is always starting on the left and going to the right. It doesn't have to, but I want, okay, I have to grade people's things, and this is going to be too convoluted for me to do if people do something else. We're always going to have our light going from the left to the right. Why? Just so everyone's doing the same thing. That's the only reason. So if I have light coming here, So let's say here's my incident light. This is my incident light. And so here's my surface here like this. This light's going to come in like that. It's going to go like this and that. Right here's my R. So here is my refracted ray. Refracted ray for the surface. Okay, if the refracted ray and R are on the same side, R is positive. If R and the refracted ray are on the same side, R positive. R is your radius of curvature of the lens.
I'm assuming your opposite side R is negative, right?
Yes.
Oh,
So this one here is going to be positive. Now, what would then a negative one look like? It's still spherical. So that'd be one like this. So here's my light. This is here. Here's my refracted ray. Where would my R be over here? My R would then be something like this. So my R is on this side. My refracted ray is on this side. This R here is going to be. Okay. It's just, I mean, it's just the way it does. I mean,
Okay, just telling you the, okay.
it's just the same way. Some R's are positive and some R's are. Okay. Let's get a couple more things. Here's another sign convention. If the object, I'm sorry, if the image is on same side as the refracted ray, the image distance is positive. So let me kind of show you that. So that's going to be something like this. So let's say here's my object. And so the distance from the object to the lens here, I'm going to call this SL. This is your object distance. Let's say I have light going like this. Let's say this goes like this. Let's say here's my image. I'm going to say the distance from the image again to the center here. I'm going to call this SI. This is going to be my image distance. Now what happens here? My image is formed over here. Okay. My refracted ray is here, so this SI will be positive. I might have something like this, and we're going to when we do the derivation. I might have something like this, or maybe I have light coming in like this, and maybe it goes like that. So here's my refracted ray. But what would happen? I would extrapolate it back like this. This right here. That's my image distance. This image distance here. I'll worry about we'll also be able to have a virtual object. I'm not going to deal with a virtual object if that gets, that seems like a problem. I don't want to deal with a virtual object. I'll show you how to, I can show you how to draw it right down there. Almost no one shows how to draw it. Okay. With that in mind, actually, let's figure out how SI, SO, and R are all. So let's ask. How are SO, SI, R, N2, and N1 related? That equation is going to be called the Finland's equation. This equation is called the Finland's equation. I'm doing this before we talk about dispersion, because basically when I get to dispersion, one of the effects of dispersion is going to be affecting this equation. I want you to see an actual real practical application of this. Okay, so we're going to use that picture and that result from homework, daily homework 7, to do this. Okay, so look at this picture here. Okay. I'm going to draw the first part of it here. So let's start with this. Can I erase this here because I want to. So let's look at this picture here. I'm only going to do the first part here. So here's this part, and that is showing up good. And here's my object here. Here's my ray going through. Here's basically my line going through the whole center of the system. And we're going to call from here to there. If you look in the diagram, that's going to be an object distance. And we're going to have 2 object distances because we're going to have 2 surfaces. So this is going to be SO. That's going to be for the object distance. And then there's going to be a 1 here because this is for the first surface. So this is the object distance. Okay, for the first surface. Okay, and if you look over here, this one here has a radius here called R1. Okay. And if you look here on this ray, I'm just going to draw one of the rays to make it a little bit easier. Basically, this ray is coming in like this. He draws another one too. Draws a little perpendicular, and then this ray kind of goes off like that. And this ray goes like that. This gets extrapolated here, back to there. Now, if you look, he's drawing 2 rays here. I'm not going to draw 2 rays just because the diagram is getting too much. Is that okay? And so this object over here, what would we call this? This distance from here to there. I'm going to take a look at this. Okay? This is going to be SI, right? And it's going to be 1 because it's for that first surface. Is that SI1 going to be positive or negative? That's going to be a -1, and that's going to become the point. So this right here, this is the object distance. I'm sorry, the image distance for surface 1. And this SI here, 1, is actually less than 0. It's actually negative. Okay. Now what we're going to do is we're going to have basically another surface over. We're going to have another surface over here like this. Okay. I'm going to actually draw that separately over here. So I'm going to draw this surface over here. And this is going to have a radius R2. So let's have a radius R2. This is our second surface. But really, it should be here, but I'm just drawing it over here. And what we're going to have is that this distance here, that's D. Okay? And that right here, and from here to there, this is my SI1, and this is my D. Okay. This image here, this image, okay, let's say the image of surface 1 acts as the object. The surface to it. Okay. And so if you come over here, what's going to happen here from this point over here? We have that ray that kind of goes like this here, and then what's going to happen when it comes over here, when it hits this side here, it's going to go like that. It goes right here. Is that even showing up? Yeah, it is. What is that going to be called? Yeah, this is going to be an S. This is an image distance, but it's for the second surface here. So I'm going to call that. This will become SI2, and hopefully you it the same. Yay! Okay. Now, where would be SO2? This right here. That distance for here is really SO2. So what would be SO2? Now I can't quite do this. I don't know why I can't quite do that. What is SI? We need this distance here. This SI1 is negative. So we really have to do that. Does that make sense? Okay. And now that we have the variables here, what we're going to do is, if you go to daily homework 7, okay, I'm going to apply basically this equation here to this surface and then to this surface. Okay, so let's do that. So according to this surface here, what do we have? So I'll put this over in the side here. I'll put this in the phantom zone. So Zephyr can't see. Whatever you do, don't tell Zephyr I put this over here. Okay. This is a secret. Don't tell Zephyr. Whatever you do, don't tell Zephyr. Okay. So what do we have here? Now let's apply to this side here. So what do I have? This side here is N1, and this is N2. So what would this become here? This side here would become what? This would become N1 over S, O1 plus N2 over SI1 equals N2 minus N1 all over R1. Does that make sense? Okay, now it gets a little more funky on this side here. Now it's applied over here. So this right here is my object. But where's that ray actually coming from? Here. So what is this index of refraction? Yeah, so this is going to become N2 over SO2. Okay, plus, now it's over here. So this is going to be N1 over SI2 equals N1. They get flipped. N1 minus N2 all over R2. See, at one time when I first got here, okay, so Dave Tues was here, David DeGraff was here, I was hired, Roger, and my other colleague was hired, Robert. And so we actually, for a while, for 6 years, had R2D2. Actually, for a while here, we actually had Nelson Mandela. we did, I'm not kidding. We had Nelson, and we had another student called Mandela. So, for a while, we had Nelson, Mandela. You just pause a little bit, that statement's true. Okay, what are we gonna do now? I don't really know. So we're gonna do things. We're gonna add. We're gonna subtract. You want to add?
I mean, we could.
No, we're gonna do the following. And this guy here is what? SI1 plus D plus N1 over SI2 equals N1 minus N2 R2. This side here is really going to be what? This is really minus N2 minus N1 over R2. Right?
Oh,
So you get N2 over SI1 plus D plus N1 over SI2 like that. I'm going to subtract these, so it's not going to be. That's right. That's right. Do that. You need a minus sign. You need an extra minus. Where am I messing up the minus sign? Well, this SI1 here, the whole thing here is that whole thing is going to be positive because here's my refracted right here, and then this is over here like that. So that's going to be fun.
can you like change the side one?
I think I even have this side here corrected. This one here is negative here, but that's you leave it intrinsically like this.
Can you rewrite side one?
Oh. No, maybe that's a mistake. True. It can only be over here. That's doing exactly what, that's going to go away. So that's true. This is all. This is all. Then that comes in. That's going to minus. Okay, I'm just going to continue. There's going to be a mistake, and I'll fix it. Let's see if it sells. I'm going to take this and subtract this guy here. So let's give this. Okay, I'm going to give this equation. I'm going to call this here equation 2. And this equation 1. Okay, I'm going to take 1 minus 2. What this gives me will be N1 over. So this gives me N1 SO1 plus N2 SI1 minus this guy here. This guy. I'll fix this up tomorrow. You get that guy here. And then this guy here comes in with the minus and the minus. That. Ooh, that. Minus. The minus, so I need it to be minus here like that. So this side over here, I can pull out this for N2 minus N1, which is correct. This is 1 over R1, and then plus 1 over R2. This should actually be a minus sign. Should be a minus sign. Don't worry. Should be a minus sign here. But then what happens here? Actually, no, these have to be added. Okay. Plus, sorry about that. Plus, plus, and then this side here is right. Well, this term has to cancel this one. Oh, it does.
Yeah.
We're fine. Okay, they just said there's no mistake. Never mind. Okay, we're okay. Good. All good.
So did you just change it to adding the two?
Yeah, we just add.
Oh, okay.
We're good. Okay, now, so is that going to, okay, I apologize for the pause here. We're going to add 1 and 2 like this. So here's this part here. And I'm going to add this part here, and then the plus sign. Then I'm going to add this part here. Add this piece here, which is really coming in with a minus sign here. That. So that gives me this here. Okay. Now, what does that give me? This gives me N1. N1 over S01 plus N2 over SI1 plus N2 over SI1 D plus N1 over SI2 equals N2 minus N1 1 over R1 minus 1 over R2. Now, what did we say about D? And it is, yeah, D is small. So this whole term here is approximately what? N2 over magnitude of SI1. What do we know about SI1 here? Negative. So what do these three terms do? They cancel. So this gives me N1 over SO1. It's N1 over SI2 equals this guy. Okay, we're going to call this one here. We're just going to call this one. Call this just SO. Hey, what do you think we're going to call this one? SI. And we have the thin lens equation in a very general form. So this gives us N1 over S0 plus N1 over SI equals N2 minus N1 over 1 over R1 minus 1 over R2. And this right here, I'll try to convince you of this on tomorrow. This is going to be by definition 1 over the focal length. F is the focal length of the lens. Okay, and often what is going to be N1? Yeah, so often N1 is air. So this gives us 1 over SO, this 1 over SI, and then 1 over R. What I'll do is I'll give you a geometric argument for that next time, which is truly virtual. Okay. But what this is going to allow us to do, this is going to show us that the focal length here depends on the index of refraction of the material. And also, if you were to take a lens and open in water, of the index of refraction. Okay, that makes sense. Sorry about that. I hate it when I hit this on a mistake, but I think there's a mistake. Make sense? Okay. So we'll see the implication of this tomorrow. Okay, have a good day. No. Put them back in their little envelopes if I gave you a little envelope. And then just save on the desk here. We'll probably use them again.